A little bit on the Zener diode. You could call this, some of it is supplemental information, but you better know it. That means anything. Supplemental means that normally I don't go into this depth with the Zener, but this time I will because I like it. Zener diodes are designed specifically to operate in what condition?
Reverse bias.
Do not, for the life of you, do not forget this. Reverse bias. Why? Why? It's made that way, yes. It's doped specifically. Heavier junction to keep that switch open over a wide range of currents. How many times have I said that? A whole bunch. So here's my definition to you. Something to put in your little hat. Got it. Maintain nearly constant. What's that? V sub Z. What is that? Zener voltage. And I also put in parentheses next to it reverse voltage. It's the same thing. If you remember that DC characteristic chart way back in BEC, everything on the left side was all the reverse stuff. Reverse breakdown voltage, reverse current, all those things. That's where the Zener likes to operate. So if there is a change in current, the Zener current that is, its job is still to do what? Keep that switch open. Open switch, max voltage, right?
Yes, sir.
Yeah, that reverse. So we must have to place this in the circuit. How? How we place that in the circuit?
Reverse bias.
It's reverse bias. Or backwards. Polarity, right?
Yes, sir.
If you think about it, you're kind of putting that diode polarity-wise backwards in the circuit, aren't you?
Yes, sir.
That's exactly what you're doing. You have to do it that way. And it can maintain that voltage, that Zener voltage, or think about the open switch concept, over a wide range of currents because, again, it's manufactured that way so it can. Look at a spec sheet. Any diode, it will give you a range of currents, a min and a max. And within that range, in the circuit, if the current changes in that range, the Zener is still going to maintain that nearly constant voltage that is designed to operate at reverse bias. The Zener diode in all of these regulators, think about all these regulators we talked about. Isn't there a Zener in every one of them?
Yes,
Even this one?
Yes, sir.
Conceptually there is, right?
Yes, sir.
Because the 3-pin, I drew that imaginary Zener to get you to think that, oh, that Zener, a constant 1.25 volts across the out and adjust pin. Hello. So basically, every one of these, we're dealing with a Zener diode. It sets the regulated output, doesn't it?
Yes, sir.
Not the input voltage. Does the input voltage, for example, this first one here, the series voltage regulator, does that set the output voltage? I don't know why it would take so long to think about it. Look at what I'm pointing at. Does that set the output voltage?
No, sir.
No! What does?
The Zener.
That's why we give you all these formulas. V out equals. And isn't it always VCR1 plus or minus the forward voltage?
Yes, sir.
That's what sets the output voltage. Look at this. I squared this in red. Sets the regulated output. Why didn't I write voltage? We have a current regulator, don't we?
Yes, sir.
But its potential in parallel with R1 in that circuit does set a regulated output, doesn't it?
Yes.
It just happens to be current this time for that circuit. But we're still using a Zener to help regulate, or not regulate, set. That's a key word here. Set regulated output. The line voltage does not do that. This does. That does. That's what V out equals, or assist in establishing what the output current is. For that one. How's that horse?
Yes, sir.
In the ditch.
Don't forget this. It's the Zener that sets the regulated output, not the line voltage. We know the difference, right?
Yes, sir.
Okay. How we doing?
Good, sir.
Good, sir.
Here we go. Moving on. Are we done with intro to regulators?
Yes,
No, we're not. This is a series voltage regulators part of that lesson, wasn't it?
Yes, sir.
Ha! No, we're not. Which one of these is a series voltage regulator? Which one?
Top one, sir. The bottom. Top one.
I hope you're kidding me.
Top one because
One that's the
transition
series.
of the
Look, it's the top one. Are you kidding me? This one's the series voltage regulator. Why do we call it that? Okay, that's good. Good answer. Stop. Just stop before you like screw it up. No, you're good. Good answer. Because what do we call the regulating element?
Series
Q1 is in series with the what? Oh, look at the redraw. Isn't it?
Yes, sir.
Don't forget what Q1's called. It's the regulating.
Element.
What else? Yes, that's its other name, the series pass transistor. Do not what? Series pass, two names. We discussed this already in the lesson and before quizzes. You should know this by now. So, for the ELOs, of course, during the beginning of all these lessons, for the regulators, we need to be able to know what each component does, right?
Yes,
The
sir.
characteristics, that is. Regulation process, that's the arrow analysis. This redraw, that's from me to you, to hopefully help some understand what's going on a little bit better. What we call R1 over there, what does it do in this circuit? What does R1 do here?
Run past the base current.
That sounds like a plan. Isn't this the path of base current?
Sir.
Q1 base. Yeah. R2 and R3, what do we call those things? They're called the series dropping resistors. Don't forget what they're called. Or R sub S, same thing. And they're there to handle current parallel with each other, low ohmic value resistors to handle current, especially when there's an increase in lines. Hey, handle that current, split it, dissipate unwanted current. And guess what? Guess how much voltage drops across those two resistors?
Not much, sir.
Not much at all. Those are combined 34 ohms, aren't they? Like 68 ohm resistors, parallel 34 ohms. How much voltage is going to drop? Next to nothing. So when it's time for the regulation process, I draw an arrow pointing to the right. Because you can prove it yourself. You should have when you did the lab. Go ahead and take your leads and place it across right here, R2 and R3. Wow, that doesn't move. It's like 15 millivolts. It is. That's why I do that, to make this a little easier, because, hey, this is relatively constant. And even in this circuit, VCR1, look at that. Doesn't this establish the base voltage for this one? Yeah. And guess what? The base voltage is not going to do much of. Rhymes with change. Whole lot. CR1, that's our zener, isn't it?
Yes, sir.
And we know what it does by now, don't we?
Yes, sir.
Yes, V out. It helps set the output voltage. In this circuit, what's the formula? VCR1, what?
Minus forward voltage.
Minus the forward voltage.
Or,
Hold on, I'm getting there. I'm getting to the or. You want to do this review?
I just want to
You know, we could do that. You can be on camera too. You want to do it? Oh, okay. All right. But I like it. You're thinking exactly what I am. But first, why do we subtract the forward voltage? It's a polarity thing, remember? Because the zener's in the circuit backwards.
Sir.
Negative is down here at the bottom, isn't it?
Sir.
Look at the source. P-type materials attached to the negative portion of my circuit. Holy crap, something's already wrong. It's backwards. This is the more positive part of the circuit. Oh, it's the cathode, so therefore you should be able to tell, all right, it is in a circuit backwards. It's a polarity. Whenever you take a voltage drop across a component, it's going to have polarity. That is what I like to call BO1 stuff.
Yes, sir.
Isn't that an NPN transistor?
Yes.
Oh, series opposing, got it. Subtract the forward voltage, do a now move. If we know this formula, and we do, 5 volt Zener, I already assigned it. But there's another formula that's the same as that. Now, what is the other formula?
The voltage of the Zener minus the voltage of the base emitter.
Does that make sense? Isn't the Zener voltage and VCR1 the same thing there, Williams? It is. Isn't the forward voltage in base emitter voltage the same thing?
Yes.
It is. Either way, it's the same thing. So for this one, 5 volt Zener minus the 0.6 gives me what kind of regulated voltage here?
4.4.
That's what we're trying to maintain nearly constant despite changes in line of load. That's the dealio. R4, what do we call that thing in this circuit? What's R4? Leader. Now check this out. I have the series and the shunt on the same board here. R4 in this circuit is not the same job as R4 in the shunt, is it?
No, sir.
Don't screw it up. Pay attention when you're asked about components in these different circuits. You need to know what they're responsible for. If you don't, you probably won't get that question right if you're asked. R4 is the bleeder. Hey, no load conditions, I unplug it. That current that existed there, where's it go? It's got to go back into the circuit somewhere. It just doesn't disappear. Bleeder. That's what a bleeder resistor is for. C1, all these capacitors, just think stability. Whenever you see something like unwanted transistor oscillations, shunts, AC variations to ground, that's what all these capacitors do in every one of these circuits. And of course, we got the load itself, which represents whatever I'm plugging into the circuit, like the gyro model. That's the load.